Okay, welcome everyone to this middle talk. Today our speaker is Ahmed Ittihad Hasib. So he's a postgraduate researcher at Warwick University. And today's topic is SL2 and its advantages and system. So yeah, now I think I'm gonna just give the floor to him. So yeah.
Thanks everyone for the invitation, both Otanu and Hongmoy. I thought I'd be a bit cheeky and like say I'm a postgraduate researcher, which is like valid, but I'm just a PhD student. Also, but that sounds less fancy than postgraduate researcher. Anyway, I'm in my second year of my PhD, and I've been working on algebraic combinatorics mainly. And like as you know, well, I don't know if you guys know much about algebraic combinatorics, but like a lot of it has stuff from Lie algebras because Lie algebras are algebraic, but their representations and the structures that they have a lot of combinatorics in them. So it's at the intersection, and which is what I do mostly. And I thought I would give a brief introduction on some of the fun algebra of it. So the plan is that I'll talk about SL2 for the first third of the talk to give an introduction to those who haven't seen this. So this might be relatively boring if you've done a course on Lie algebras, which you may have. And then I'm going to move on to talk about the quantization of it or what that even means. I'll relate how the quantization comes back to SL2 so whenever I refer to classical SL2, I'll talk about SL2, which is the definition here. But when I talk about the quantum stuff, it's going to be something different. And then for the third part of the talk, I'll talk about some like combinatorics that come when you look at the representations of the quantization. Having said that, I'll get started. Also, I hope this is like fairly informal and you can like pause me, I don't know, interrupt me and yeah, ask any questions that you may have. Cool. So SL2 is, as I said, it's all 2 by 2 matrices which has trace 0. And then we have a binary operation on it, which is given by the commutator. Now, a sanity check on this is to check that if you take 2 trace 0 matrices and take the commutator, you get a trace 0 matrix, because if you take the trace of this and the trace of that, they're going to be the same because of the property of trace being cyclic. And then it cancels out. With this operation and this set, we get the Lie algebra SL2. I'm not going to get much into what a Lie algebra is, but this is the canonical example of a Lie algebra. It's the smallest nice Lie algebra, which also happens to like kind of lie at the core of every other Lie algebra. If you've taken a course on Lie algebras, you will have seen something about root systems of Lie algebras, where each of the root pair is a SL2 pair, and then the way they are aligned dictates the whole Lie algebra. But for now, we live in a fun world of just SL2, nothing complicated. Okay, so yeah, you can fairly easily see that as a vector space, this is 3-dimensional. I'm going to quickly write down some basis elements. So this is, I always get this wrong, so please correct me if I'm wrong. I have no confidence in my ability to get E and F right. And then H would be given by 1 minus 1, 0, 0. I've gotten this wrong like half of the time, which is like kind of impressive. It's a basis of the vector space, and if we determine the Lie bracket on these like pairs of elements, we will be able to like compute it for every element in my SL2, because we can just expand everything in terms of these 3. So I'm going to quickly write that down as well. So if I take H and then E, I should be getting 2E. HF should give me 2F minus 2F, and EF should give me H. This computation literally involves taking the matrices H and E, multiplying it this way, the other way, and then subtracting, and you should be able to get 2E back, and so on. So another way to define SL2 is to say that it's a three-dimensional vector space with like abstract bases E, F, and H, such that this holds. And that would also be a way to like define SL2 instead of like having concrete matrices. Okay. As I said, I work in representation, so I'm gonna give a definition of the representation of a Lie algebra of SL2. So a representation of SL2 on a vector space V. Everything I'm doing for the first third of the talk is over complex numbers. So this is over C. It's given by a map rho going from SL2 into the endomorphisms of linear operations on V. It's a fancy term for matrices that send things from V onto V itself. So if you choose a basis of V, if your vector space is finite dimensional, which it will be for all of my talk, then if you choose a basis, this is literally a set of matrices, n by n matrices, if your vector space is n-dimensional. This is a small L. All right, so it's a map from SL2 onto the endomorphisms such that this is true. For all A, B in SL2, we have a structural thing happening. So if I take the commutator, we should get rho of A, rho of B, and minus rho of B, rho of A. Oh, thank you. Yeah. All right. I'll quickly give an example of a representation. The canonical one would be our first example. Oh, this is nice. Example 1 is C2. Oh. What? Oh, yeah. I don't. Is that lighting an issue with the camera? Ah, okay. Ah. Okay, fair enough. Maybe you could like turn on a light in the background, maybe. I don't know, with those ones. Oh, that's yeah, fair. Let me do. There's not much happening. It's just a vector space V. Let's see. Now this is good. I'll use this one. All right. So we have. I'll take the canonical example, which this is a standard representation of SL2, which is two-dimensional. Any guesses from people who haven't seen these things before how SL2 acts on this? Only from people who hasn't seen. Oh, wait, has everyone seen SL2? But who hasn't seen SL2 stuff? Raise your hands. Okay. Maybe I'll go through this quickly. Okay. So on C2, this works as the matrices. You take a vector and then you multiply by the matrices, and that's how SL2 acts on a two-dimensional vector space. So for example, if I have the vector 1, 0, this is E1, then E acts on this. Okay, I don't need to do this. E acts on this by, give 0, 0, 1, and H should keep it same. Yeah. And so on. You can compute the other vector as well, the other basis vector as well, and yeah, you get a representation. This is a special vector in the language of SL2 stuff, because this is when you act on it by E, you get the null vector, and when you act on it by F, you end up with the other basis vector. these types of vectors in general are called highest weight vectors, where when you act on it by E, you get 0, but when you act on it by F enough times, you end up with all the vectors in your V. In this case, C2. And like the highest weight vectors, so I'll write as HWVs sometimes, dictate the representation theory. All right. Okay, what am I doing? This one.
So the highest weight vector is also called a cyclic vector.
Really?
Yeah.
I mean, it is a cyclic vector because like it generates everything, right? Because the definition of a cyclic vector in representation is like it generates everything, but it's so much more than a cyclic vector, right? I don't know. Like, if you had three vectors, like any vector would be a cyclic vector in an irreducible representation, right? Or I don't know. But yeah, no. Maybe I haven't seen that though. Right. So let me move on to some like quick facts about SL2 representations. So SL2 is, firstly, it's semi-simple. What that means is that when you have every representation can be written as a direct sum of irreps, irreducible representations. So this is kind of like a Maschke type theorem if anyone's done representations of groups, which is fun, but like, I don't know. I don't like it. It's too complicated for me. Okay, and then crucially, for all n in 0, there exists a unique representation of Vn of dimension n of dimension n plus 1, which is irreducible. Okay, and then for each of the Vn, they're structured quite nicely. Like if Vn looks like this, I'm gonna do in quotation mark. You have a highest weight vector. Let's say this is V, and then you can just apply F enough times. So if you should be able to apply F n times to get like F of V. This is F square V, and so on up till F to the n V. And these are the vectors. These form a basis of a Vn. Any questions so far?
The last.
Okay, so the last line is talking about the structure of these Vn's. The Vn's are the irreducible representations, which are representations that cannot be divided. Like you can't write them as direct sums of two representations. And the irreducible representations for SL2 can be characterized by the dimension. For each n, there exists a unique irreducible representation up to isomorphism of dimension n plus 1. Yeah, I could have just indexed it as like from 1 and say dimension n, but there's a reason for this. So for example, this is isomorphic to V1. This is an irreducible representation. You can't divide it. You can't have subspaces of this, which are representations on their own. And each of the irreducibles look like this. Does that make sense? Okay. Quotation marks. Yes. So if you apply F once more, this is going to be a lowest weight vector. things a bit more, but each of the weight of a vector is kind of like the eigenvalue when you apply when you take the operator h on each of those vectors. But let's not go into that. Okay. Combining well, I didn't number them, but like the first one and the last one, what you have is that when you for any representation, you take a collection an independent collection of highest weight vectors, and you lower them by f, and you get like a string of vectors. So you take, for any representation, not just irreducible ones, the picture that you get when you do things like this is that you have some highest weight vectors, and then you apply f a bunch of times, and then you end up with 0 eventually. And then for the next one, you do the same, and so on. So the way to get a decomposition of a representation as into irreducibles is equivalent to finding the highest weight vectors. You find the highest weight vectors, and then you let f go through the rest of them. This picture will be very, like, I'll focus on this picture a bit more with a precise example right now. On board 4. Sorry, is this confusing? I'm gonna move this to like board n-3 every time I write on board n. If that is confusing, I will not do that. But I thought I would do this and save myself a bit of time. Okay. Example 2. So this time I'm gonna look at C2 tensor C2, which is also like, you could say this is V1 tensor V1. So for those of you who haven't seen tensors before, think of it as kind of like multiplying vector spaces. It's a bit funny, but I'm gonna write a neat basis of this. So if I name, let's say x is my vector 1, 0, and y is 0, 1, then C2 tensor C2 has a basis given by x tensor x, x tensor y, y tensor x, and y tensor y. Yeah, so it's a 4-dimensional vector space, 2 times 2. And what else? Yeah, this is also a representation coming from the co-product of SL2, which I'm not going to go into, but the way an element G of SL2 acts on A tensor B by doing it on the first term and then doing it on the second term, like Leibniz rule. It's precisely Leibniz rule, which I'll mention in a bit because it's like physicsy and I don't understand it. But yeah, so it acts on it by doing this. Okay, you take G A tensor B plus A tensor G B. This is because Lie algebras are somehow like, I don't get this, someone may do this better than me, but like Lie algebras are somehow derivatives of Lie groups. I don't get it. But when you take a group and you take tensors of them, you've seen it in representations of like groups maybe. On the tensor product, the representation acts on component wise. So G tensor G. If you take the derivative of G tensor G, you get like G tensor 1 plus 1 tensor G. So yeah, this is how representations, the tensor of representations work in Lie algebras. So yeah, using this, we can see how E and F acts on this. I'm going to write the highest weight vectors down because I have them memorized. You'll see that x tensor x is a highest weight vector because if you act on by E, what happens is that like this x goes to 0, that x goes to 0 in the other component, so we'll get 0. And the other highest weight vector will be given by x tensor y minus y tensor x. To see this, apply E on there. When you apply E here, you get a 0. When you apply E there, you get x tensor x. So if I do E of the whole thing, I get, well, I'll just write this down. Y tensor x, I will get x tensor x from the first term, and then I'll subtract x tensor x again. This is a bit confusing, but yeah, we get 0. Right, so these are the two highest weight vectors. And then to get the whole decomposition, we lower it by f. if you lower this one by f, you will get like a similar situation where the component there becomes y tensor y. This one, the term there is y tensor y. This one is y tensor y as well. So it cancels out. We get a 0. So I'm not going to write anything more. But for this one, we get something like x tensor y plus y tensor x. And then next, I get 2, but I want to rescale this, just y tensor y. Is this clear so far what I'm doing? Cool. Any questions? Oh, okay. So yeah, after this, I can clearly see that there's 2 components to this representation. So if I can write down the decomposition in terms abstractly. So V1 tensor V1 is isomorphic to V2 because this is the 3-dimensional one and there's a 1-dimensional one below. V2 direct sum V0. And in general, there's like there's the Clebsch-Gordan, it's a Clebsch-Gordan formula, which I mean, you can use that to easily compute the tensors of 2 representations. So what I'm doing is like it's fairly elementary, but it's fun. Okay. I'm so sorry. Okay. So I'm going to move on to the quantum group. Oh, I'm on time. Nice. I'm going to move on to the quantum group EQSL2. I may swap between saying quantum group, quantized Lie algebra, and some other terms that involves quantum. I don't do physics. I'm sorry, but I don't know why it's called quantum. It has something to do with quantum integrable systems, but I don't get it. So please don't attack me if I get something wrong about the physics side of it. What happened is that in around like 1985, people like some crazy Russian mathematicians figured out that you can do what I'm going to show you and get a bunch of results in, wait, what is this? The Yang-Baxter equations? Yeah, if that floats your boat, okay, go for it. Yeah, so, and then they solved the quantum Yang-Baxter equations using this, but around 1990s, some other crazy Hungarian and Japanese mathematicians figured out that you could use the same object to study representations and get like fun combinatorics, which is what I'm interested in, more so than Yang-Baxter equations. Okay. So the quantum group, or the quantized Lie algebra, EQSL2. I'm gonna write U for the most part. Yeah. Let's define this. So I'm gonna write CQ as the fraction field of a single variable. So PQ such that A, B are polynomials over Q. B non-zero. Yeah. Then EQSL2 is an infinite dimensional algebra over CQ. So my field is CQ now. I've left the world of complex numbers. I've added like an indeterminate. So I've got this is quite nasty. Well, it's not that nasty. It's still characteristic 0. It's nice. We do not like positive characteristics. Actually, I'm speaking so much propaganda. With generators, E, F, K, and K inverse. And then I've got like a bunch of relations, which are, so K and K inverse multiplied together is K inverse times K equals 1. K inverse equals Q square E. KF K inverse equals Q to the minus 2 EF. And finally, EF minus FE equals K minus K inverse over Q minus Q inverse. Okay, so it's not too bad, but it looks intimidating, I think, if you haven't seen this before. The way to motivate this is, so I just like got rid of the definition of SL2, but if you remember what the definition of SL2 was, it's gonna be something like you had like E. If you take the commutator with E, you get like some 2 there, you get a -2 for F, and blah blah blah. So it resembles SL2, but it's slightly odd still. Yes.
You were in the setup of Lie Algebra. Now you are in the associative algebra.
Yes.
So, did you have to go to the Universal Enveloping Algebras first?
Yes. Yes.
So you not saying about that or way to Universal Enveloping Algebras.
Yeah, that was gonna be my next slide because I'm gonna bring it back.
Then you were informed that
We're deforming the universal enveloping algebra. Yes, that's how you do it. I don't think.
this is the deformed.
Yeah, this is a deformed algebra. Yes, it's not the universal enveloping algebra because I was debating between like either starting with just the USL2 instead of SL2.
The associative by universal and then deforming it.
Yes, precisely. Yeah, that's I believe that no one's like deformed Lie algebras on their own. You get the associative algebra and then you deform it. Yes. So I'm gonna briefly mention how this relates. This is fine now.
And then people recap with this field C sub Q.
Oh yeah. So C sub Q, it's the fraction field of single variable polynomial. So yeah, it's like you take the polynomials and you that's a ring, and then you take the fraction field of that ring. Yeah, I wrote it too literally, I guess, and that's a bit confusing. But it is genuinely just like rational functions over complex numbers and single variable rational functions over complex numbers. Yeah, so there's a lot of like different things you can do with values of Q. For us, Q is an indeterminate. So all the things that we do would translate. So if you want to work over just complex numbers, all the things that we do would translate over Q that's transcendental. So it's definitely not roots of unity because that gets into like algebraic number theory, and you get like things that are very similar to like finite field Lie algebra stuff. We like complex numbers. Okay, this is probably not ideal. Okay. So I'm going to try to relate this object that I've like constructed back to SL2. I won't do SL2. I'll get to the universal enveloping algebra of SL2, which is a closely related associative algebra of SL2. There's a construction that takes a Lie algebra and gets you and spits out an associative algebra. And there's also a theorem that says that the representations of that algebra corresponds like 1-to-1 with the representations of the Lie algebra. So when we look at the world of representations, we don't lose or gain anything from switching from SL2 to the universal enveloping algebra of SL2. I'm not going to define the universal enveloping algebra. I'll just like quickly sketch how you get USL2 from UQSL2. So this is limit at Q equals 1. This is the physicsy part of this. Like people were like, oh, we can evaluate certain values of Q. We can take certain values of Q and get like different algebras. Let's try to think about what happens at Q equals 1. Now, if you directly like evaluate Q equals 1, you get chaos, because if you put Q equals 1 there, it's like something over something divided. You're dividing by 0, which is not what you want to do. So you do L'Hopital in a way, because when you when Q tends to 1, K and K inverse become similar operators. So it's a 0/0 situation, and you can take the derivative of that. I'm gonna sketch the solution, sketch the proof somehow. if I can. So you consider a variable h bar. It's standard. I know it's confusing with the h's over there, but I'm sorry. So that q is e to the h bar, or like, it's like 1 plus h bar plus h bar over 2, and so on, like the Taylor expansion of this. And we look at the ring of formal power series over h bar. So this is like the polynomial ring, but we're including infinite terms. I should be including negative ones as well. I'm not sure. Yes, my bad. Yes, okay. So this is the Lorentz series, that's the one. Okay. And then if I have this situation, then we clearly have CQ lying in this, because Q is e to the h, this lies in it, and you can, like, if you multiply and divide by any Q terms, that also lies in this. So this is a larger ring of this field. So we're going even larger than CQ. I know it's uncomfortable, but we've got this. Okay, and then we extend the scalar. So we take U and we take the tensor over CQ of like C of this large ring, and this we define to be UH. Now, if you look at the algebra UH and you quotient out by H times UH, I'm not going to compute this, but you will get the this as an algebra will be isomorphic to USL2, which is the universal enveloping algebra of SL2. This involves a bit of computations with seeing how these act under these scalar extensions and quotienting out by H times UH. Heuristically, this is saying that we let H be 0, and if you let H be 0 there, we're evaluating Q to be 1, heuristically. Any questions on this? This is not a proof. This is like just kind of vibe coding, but maths. Yeah. Okay. Aha. I've lost count. Second?
7.
Yeah. Oh yeah, this was 6. Yes. Oh yeah, we're doing mod 4. Of course it's 6. This is 7. So much maths. Okay. Oh, actually, this was very good. Pretend I didn't remove that. So representation theory of of UQ-SL2, just because of like this relation, has all those properties as well. It's semi-simple. I'm gonna lie slightly and say there's a unique representation for each dimension. There's actually 2, but like we don't care about the negative ones. We only care about the positive ones. So there's a unique representation Vn, which I'm gonna write as Ln now, L plus n, which is irreducible, and they look like this as well. The representation theory of UQ-SL2 is exactly the same, except that like there are some Q's popping up, which we'll see, which is what makes the combinatorics interesting soon enough. Okay. So all that I said about SL2 on this slide was true. Like when you have a representation, you look at the highest weight vectors, which are the null vectors of when you apply E, and then you lower by F, blah, 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 and you get a picture like that, which we had for, like, I think in that example, we had a picture like that as well. But that was for SL2. The same holds for EQ-SL2, which we'll see soon. Okay. Right. Example time. So the standard, this is example 3. The standard representation of EQSL2 is 2-dimensional, and so that's going to be like CQ square with basis x comma y, and then I will spell out what the actions look like. Yeah, E of x is going to be 0, E of y is going to be x, f of x is going to be y, f of y is going to be 0, k of x is going to be x, of y is going to be, ooh, my bad, sorry, qx, and q to the minus y. So to see that this is a representation, what you need to check is you need to check that like on both sides of the equalities, if you take k inverse of any of the vectors, it equals q square e of any of the same vector. I'm going to do one quick check just to see that like we get the same thing. So let's look at EF minus FE of x, right? So E applied to x is 0, so this is going to be 0. The next one is going to be F applied to x, which is y, and then E applied to y, which is going to be x. So this whole thing is x. But on the other hand, we get like k minus k inverse divided by q minus q inverse. So k minus k inverse divided by q minus q inverse of x. You apply k inverse on x. Well, I didn't write k inverse down, but it's going to be the inverse. So k inverse of x would be q inverse x. So we get k times x minus k inverse times x divided by q minus q inverse, and it's going to be q minus q inverse x by q minus q inverse. So like you to prove that this is a representation, what you do is to kind of check that these things, the equalities, give you act in the same way, and that will prove that it's a representation. I mean, there's obviously so much more. I'm not going to prove it, but yeah. Again, for this, there's like you can see the picture, right? If you take x, that's our highest order vector. You apply f, and you're going to get y. And it's a two-dimensional representation, so you only have this and nothing else. And there. Okay. Continuing on with the example, I will quickly do the equivalent of the tensor. Okay. Now, as I said earlier about how tensors of representation work in SL2, a similar thing works here, but it's no longer one tensor G plus G tensor 1. There's some, you need to tweak it slightly to make it work. Since it's not part of the talk, I'm going to just like quickly write down the formula of the tensor product. So the way tensors work is by the coproduct, and the coproduct of E. You can choose many, but the canonical one that people choose is this. So this is going to be K tensor K. This is going to be, oh no, this is my bad. I haven't given myself much space. I'll give myself this much, okay. E, F, K. This is 1 tensor K plus K tensor 1. So the K's act as it does in SL2, but for F, it's F tensor 1 plus K tensor F. So there's a K there instead of a 1. And for E, oh boy, it's 1 tensor E plus K inverse. Nice. Someone help me. Thank you. I appreciate E. And there are like other versions as well. This is not even like the only coproduct that works. But for every other ones, they kind of give you isomorphic cases. So it's fine to work with one. The reason why I want to do this is because I'm going to lower this with F. So I need the formula for this. K is a group-like element. Yeah, yeah. Yes. Yes, it's K tensor K. Yes, K is a group like element. Yeah, right. My bad. Okay. Right. So let's look at the high speed vectors here, right? Again, the high speed vectors, one of them is going to be x tensor x. The other one is, I think, going to be x tensor y minus q y tensor x. Okay. If I lower this one, I don't get anything. I get a 0, so I'm not going to write it down. But if I lower this, using this formula, I lower f. I apply f on the first one, so I get y tensor x plus I get k applied on the first one, and then f applied on the second one. And k applying on the first one would give me a q, so I would get q x tensor y. And then for the last one, I would get I'm going to write y tensor y down, but what I actually get is q plus q inverse, which is the quantum 2. I'm just scaling it down because we don't need the 2. But it's kind of similar to the 2 we had in that situation, but we get a quantum 2 instead. Also, there's too many quantums happening. I don't like it. If mapta, if acts on x and y as that, and then we use the co-product to get the action. So when I'm applying f on this, f on this is going to be like f tensor 1 plus k tensor f. So for the f tensor 1 term gives me this, because f tensor 1 acting on x tensor x means it's f of x tensor 1 of x. Right? So you get y tensor x as that term. And then the second term, the next term is going to be k tensor f. So we'd have k acting on the first one and then f acting on the second one, which would give me a q for the k, and then this would go into a y, which is giving me q x tensor y. So this is all like very, very descriptive so far. The reason why I wanted to do this is because of crystal graphs. If I have time, which I may do, I will give you a precise definition of what that is. But if we evaluate q to be 0 now, what do we get? We get something quite nice, right? If we let q be 0, we get rid of this term, and then we get rid of this term, right? And all the terms we get are simple tensors. The tensors that form the basis of CQ tensor CQ. So one might hope that doing this q equals 0 move. So this is q equals 0. Doing this q equals 0 move would give me a combinatorial way to describe what's happening here. I mean, in this case, it's very simple. We can compute this, but I'm talking about higher tensor powers. Like I'm taking the tensor square here. And what if I took like CQ tensor CQ square tensor CQ square and up to like n times? In the classical scenario, we don't really get we can't keep track of it all because the terms get very complicated. But in this, maybe after we let q be 0, we can do that, which is what I'm gonna show hopefully. 0. So q1 would give me the classical situation. q0 gives me the combinatorics. So I don't like saying it because I don't understand it, but people say that the UQ stuff. Yes. So there's some caveats, which is why I'm going to introduce it properly. It's taking 0 in an algebraic geometric sense, where you have a module m and then you do m mod qm, if that makes sense more. Yeah. So evaluating at 0 in an algebraic geometric sense. Which is also what's happening in here, like we're evaluating at 1 in an algebraic geometric sense. So the q equals 0 would give me the combinatorics, q equals 1 gives me the algebra, and all of this is like a bridge between the algebra and the combinatorics in like a storytelling mode. Right. So with that, is this clear so far what I'm doing? In this, I'm just evaluating q to be 0 in this diagram. There's nothing, which is not what I should be doing, but it works for here. For higher tensor powers, I will actually end up getting like q inverses. So I would need to do the formal stuff, which I'm going to define. Yeah. Yes, the braiding thing is giving me the q's. I mean, so braid groups are involved, but not in this case. This is the quickest answer I can give, but we can talk later, maybe. About again, what I want to emphasize is that the powers of the positive powers of Q's showed up in different terms. So we didn't when you set Q to be 0, we didn't get like y tensor x twice. We got y tensor x for the first thing and then x tensor y for the second thing. Yeah. Okay, let's move on to board 4, which is board 8 now. Do I need this now? Okay. Crystal bases. I think the guy who invented this got a Nobel Prize. No, got the Fields Medal. No, the Abel Prize. I don't know. Okay, you need to be young to get a Fields Medal. You got the Abel Prize last year, and then someone from MIT went like, "No, I invented this. He stole it from me." It's like a big drama right now. Kashiwara and Lustig are the two people involved in this drama. It's like doing rounds on Reddit if anyone's like interested in math drama. But it's cool stuff. I don't know who invented it. It's still cool. Right. So let curly A be a subring of CQ given by the rational functions that can be evaluated at 0. Does that B of 0 is not 0? Right? So it looks like the denominators have because if it's non-zero at 0, then there's a constant term for the denominator. So you can precisely write it as like things that look like of A of Q plus times divided by 1 plus BQ, like things that look like this. This forms a subring of my field of rational functions, and all the representations that I'm looking at are vector spaces over this. So it's gonna be a module over this. So V, a representation, U representation is a module over curly A. That's a bad curly A, but yeah. Look at the Eiffel Tower. I should stop. Okay. A crystal base. I'm gonna switch to another one.
Use the blue one.
Yeah, okay, thanks. I'll write in blue. Oh, that's nice. A crystal base for V is a pair L comma B, so that L is free a submodule of V with V being equal to CQ tensor A of L. So L is a free A submodule, which means that it's free. I don't know how else to say it. And also, like if you extend L to if you extend the scalars of L to include all of the field, then we actually get our representation back. So L, if you've done some lattices, L is precisely a lattice of V. Like think about the lattices on R2 of natural numbers. So n square lies in R square, and then Z square lies in R square, and then Z is kind of like the A here, and then the R is like the CQ there. If that makes any sense. Any questions on the definition on the first topic, on the first point here? Okay. It has to also satisfy many more other things. B is C basis of L by QL. So if you look at L, so if you look at L over QL, L over QL is a module over A over QA. There's some funky stuff happening, but A over QA is precisely is isomorphic to complex numbers, right? Because you're looking at you have A and then you're quotienting out by QA, and QA contains everything where the numerator has 0 constant term. If you mod out by that part, then you just get complex numbers. Yeah. So L over QL is a pure vector space over complex numbers, and B is a basis. B is a basis of that. Moreover, the actions of like E and F work on this, and we're going to have some constraints of that. It's still going to be board 8, unfortunately. Okay, and then furthermore, we have E times L is going to stay within L. Okay, I'm going to quickly write that and not explain what that is. F times L is going to stay within L. E times B is going to be within B union 0. And then F times B is going to be B within B union 0. And finally, for B and B prime in B, E tilde times B equals B prime means F prime B tilde equals B. Okay, I've written a lot of garbage down. Let's try to comprehend what's happening. E tilde and F tilde are called Kashiwara operators. They're modified operators from E and F. The modification only happens by scaling on the weight vector. So it's nothing crazy. It's just scaling appropriately on the weight vectors. So as I was saying, I was scaling in this. I took like a quantum 2 away. That operator takes that quantum 2 away. So it's not doing anything too crazy, but it's not exactly E either, and F. And what this is saying is that on the lattice, E tilde and F tilde act as a closed set on the lattice and on B as well. Well, the induced action of E tilde and F tilde are closed on B, well, if you include 0. But the most crucial part is this. This is for all. The most crucial part is that if E sends B to B prime, then F sends B prime to B on this side. So, all right, let's take a step back. I'm looking at vector spaces that are finite dimensional. So my B is going to be finite dimensional. These are going to be vertices of a graph, and these E tildes and F tildes give me some edges. Okay. And this is where the quantization is happening. This is where we're evaluating Q to be 0 because we're doing this thing, which is the formal version of evaluating Q to be 0. And when you do this, okay, what was I saying? Yeah, when you do this and write down the graph, the connected components of that graph will give you the irreducible representations. So the decomposition into irreducibles of that representation. Because well, okay, I'm not going to explain that. Any questions on the definition of a crystal base so far? It's a handful, I know, but we're gonna look at one example. Okay, the reason why this is nice, well, the reason why this is useful is this following theorem. This is the only theorem that I'm going to mention. Okay, And all of this is true in generality, not just to like SL2, but we'll look at examples for SL2. Let V1, V2 be U reps with crystal base L1, B1, and L2, B2. So these are two crystal bases for V1 and V2 respectively. Then the tensor product V1, V2 has a crystal basis given by crystal base given by L1 tensoring over our ring L2, comma B1 tensor B2. So when I have tensored vector space, when I have tensored representation, I can look at the individual components, find the crystal base for that, or find the crystal base and the crystal graph for that, and then then the tensored then the crystal base for the tensored representation will be precisely taking the tensors of the individual vectors that I had in my previous crystal base. So for the final example that I wanted to do is, do I have it there? Oh, it's just there. Fair enough. Involves okay. Involves CQ to the n, right? Well, sorry, CQ square tensor to the nth power. So you can, yeah. I think we need this too. So you can see that CQ square has a crystal base given by just like X and Y. You could see that X and Y satisfies all this. I'm not going to go into it. It's very simple to check. Like we don't even need to go into like E tilde and F tilde. You can see it just from E and F because on CQ square, E tilde and F tilde are the same as E and F. And we get a graph like this, X goes to Y. Then from the theorem, what we get is that CQ square to the nth tensor has a crystal base given by simple tensors, because we can just take the tensor power of length n. This doesn't tell us much. And I'm not going to do the algebra either, but I'm going to show you what happens when we do the algebra and what the arrows are. So to get the graph, as I said, okay, I don't know where the graph is. To get the graph, we need the vertices. This theorem says what the vertices are. The vertices are going to be simple tensors. And for sanity check, this is a 2 to the n dimensional vector space. And there are 2 to the n simple terms of X and Y. So for each term, you can pick X or Y, so you get 2 to the n terms. So this theorem tells us what the vertices are in the diagram that I wanted when I set Q to be 0. And if you do a bit more work, you have to do it. It's kind of dirty, but like if you do it, then you can actually figure out what happens when we evaluate F tilde on one of those simple tensors. And what happens is this like really nice combinatorial rule, which I will describe for like a particular example. So let's take the term X tensor, Y tensor, X tensor, Y. What do I do? Tensor X, maybe, yeah. So this is a particular example where n is 6. No, yeah, 6. And then when we apply F tilde to this, the way to do this is to convert every X into an open bracket and every Y into a closed bracket. And then you look at the first open bracket that hasn't been closed yet. So this open bracket has been closed by this. This open bracket has been closed by this. And then there are two open brackets remaining, which haven't been closed. And we look at the first one. And then we turn that open bracket into a closed bracket. So that open bracket into, closed bracket. So we get this diagram. And then we convert that into y, x. I won't write the tensors down. Y, x, y, x, y, x. And then you can do this rule for every simple tensors. And it's a very combinatorial rule. And once you do it for all the 2 to the n, once you do it on all the 2 to the n tensors, you get this diagram, which gives you a graph, which gives you the decomposition of the representation. As a final remark, this is all like this decomposition can be, you can obtain this decomposition without doing this quantization stuff, but for more complicated Lie algebras and more complicated representations, you get much more fun and, like, I guess, complicated combinatorial structures coming from the algebra there. Yeah, that's about all I have today. Any questions?